Hey guys, welcome back. I'm going to take up some homework. This is Unit 4, Handout 12. It's question number 4. I'm going to take this one up because it's a little different than the other ones that we've been doing. Let me talk about it first for a second. First thing I want you to notice is the transformer is back. No big deal, okay? You'll just have to bring the voltage out to the load and figure out what's going on with the load. The second thing I want to talk about is the fact that this capacitor here is in series, okay? So that capacitor there is the power factor correction capacitor, okay? There are 3. And so what this really is an RL series circuit, and then in order to correct the power factor, they've added a capacitor in series in order to improve the power factor. Now, this is rarely done, okay? We've already talked about the fact that in order to do power factor correction, 99% of the time, you're going to have the capacitor bank out here in parallel. And the reason for that is because if it's in series like that, it does 2 things. It interferes with the load because, you know, if you put anything you put in series with the load is going to drop a voltage, and, then the voltage dropping across the load is less predictable. The second thing is when you add a capacitor in series with the load, instead of reducing the current in the circuit, which is usually our goal when we do power factor correction, it actually increases the current in the circuit. Now, in order to illustrate that, I'm going to switch over to this single phase load because that's easier, guys. And what this is actually used for, putting capacitors in series with the load in order to improve the power factor and increase the current is usually done when we're doing some kind of induction heater, okay? So an induction furnace or an induction welder or something. And then, for that matter, an induction cooktop. When we're talking about an induction furnace, what we're trying to do here is create a giant coil that we can put a piece of metal in and then connect it to AC, and the magnetic hysteresis and eddy currents that gets induced in the steel, you could actually use it to weld or melt that steel. All right, guys. So, this is a big scrap facility or a steel foundry or something like that. They're melting cars down. They build a big inductor. They dump cars into it, and they flip this thing on, and the magnetic field melts the cars, and then they pour it, and they make a new car out of it, let's say, okay? So let's imagine for a minute that this is my induction furnace, and it's single phase because it's easier to see what's going on with this single phase. And so it's a big inductor, and it's got a little bit of resistance, not much because it's a giant, copper bars that make up this thing. And if we look at this situation, if this was our induction furnace, we could figure out what's going on with this circuit. I would have a little tiny bit of, R would be equal to 1, right? And then I'd have an inductor, which is XL. Go right off the top of the page here. XL would be 1800, right? It's a giant inductor. And the problem with this is, look where Z is. Z would be sitting right here. And if I did the math, I would find out that Z is also 1800 ohms. It's going to be just a little bit over, but the resistance has, very little effect. If you go 1 squared plus 1800 squared square root, you're going to find out that it's 1800 and some decimal point, really small amount over 1800, okay? And so if the impedance was 1800 for this circuit here, then I could calculate the current. I would be equals Z over Z, sorry. And so it would be the 600 volts that I've applied over 1800, okay? And if I calculated that, I think it comes out to 0.33. Let's try it. 600 divided by 1800. Yeah, 0.33. Pretty boring, amount of total circuit current. And I'm not going to melt any cars with 1/3 of an amp, okay? And so what they do, the other thing about this is that thing has a terrible power factor, okay? This is almost 90 degrees, okay? So it's almost a power factor of 0, all right? Where a power factor of 1 is unity, right, guys? So what they do here is they put a capacitor in series, and they make it equal to, or close as possible to, the inductor. And so now I end up with this sort of circuit. And what that's going to do is improve the power factor for sure. But more importantly, it's going to increase the current significantly, because now if I, draw this circuit, R is still equal to 1 ohm, right, guys? And then Our XL, which is super tall, is still 1800 ohms. But now I've added a capacitor, XC, which is also 1800 ohms, right? So XC is 1800 ohms. And my Z is actually equal to 1 now, okay? Because there's Z, and it's equal to 1 ohm. And so the phase angle here, guys, is going to be 0 degrees. But look at what's going to happen with my current. I is going to be E over Z, so it's going to be 600 over 1 now. And so it's going to be 600 amps, okay? And if I want to use this coil to melt cars, guys, I'm going to need a lot of current, okay? Because I need a giant magnetic field that's changing all the time. And it is the hysteresis, or the, when you change the polarity of the magnetism of a piece of metal, it warms up. That's how induction furnaces work. That's how induction cooktops work. And that's how induction welders work, okay? They use magnetism to heat the steel. All right. And if I want to do it, I need a lot of current. And if I don't add my capacitor, I have two things: a terrible power factor plus hardly any current. And in this particular case, our goal is to improve the power factor and increase the current. And if I add my capacitor in series, I will accomplish those two things. Okay, so that's why you might see a circuit like this, where I've added a capacitor in series with my inductor in order to improve the power factor and increase the current, probably because this is an induction furnace of some sort. We're not going to worry about it though. We're going to calculate it. And so let's look at it. One thing at a time. E-line primary is 980 volts. It's asking about E-phase primary. It's going to be 980 divided by root 3, right? Because it's Y. So let's do that. 980 divided by root 3. It's 565.8 volts, okay? E-phase secondary, we're going to go across the phase at a ratio of 3 to 1. So that's going to be 565.8 divided by 3. 188.6 volts, okay? E-line secondary, guys, this is 188, so that's going to be 188. It is delta after all. Okay. E-phase load, look, it's delta again, 188.6 volts. Okay. I-phase load, now I need to draw a phasor diagram for that load. So here it is. Now the problem is I don't know XC yet, but maybe we can do it. Let's try it. R is equal to 217 ohms, okay? XL, 145 ohms, okay? Now XC, it exists. We don't know what it is, but it sits like this. And by the way, this phasor diagram is for one of these three loads, right? Because that little resistor is 217 and that inductor is 145. Same with these ones, but we're drawing a phasor diagram for this phase. Okay, there's XC, guys. I don't know how long it is, but I do know that Z is going to sit here, and we're going to end up with, it says the power factor for this whole thing is 0.95, so it's going to look like this, right, guys? And this is going to be X. And maybe I can calculate, Z and X, and therefore XC. And, just like VA is P over the power factor, this Z, guys, is going to be R. It's the adjacent over the power factor, over the power factor. And so it's going to be 217 over 0.95. And if I do that, 217 divided by 0.95. Looks like my impedance for this circuit is going to be 228 ohms, okay? And now that I've calculated that, I can calculate X. It's going to be that squared minus 217 squared equals root squared 71.32 ohms. Okay, guys? And then that allows us to calculate XC because XC is going to be 145 minus 71. All right, guys? So it's going to be 145 minus 71.32. That's going to be the capacitor there. And I don't know, maybe I don't have to calculate all that, but I'm going to finish this off. I think I'm going to need it eventually, so let's just finish this off. Never start a phasor diagram and leave it before it's finished. 145 minus 71.32. Okay, guys? 73.78 ohms. Okay, so that's the capacitor. Okay, but we'll get there later. All right. Now, what I really needed was this impedance to calculate this one, right? I phase load, guys, is going to be E phase load over Z of the load. Okay, so it's going to be E phase load 188.6 over Z 228. Let's try that. 188.6 divided by 228 equals. Looks like it's only 0.827 amps. Okay, guys, and then we can take that current. Not much of an induction furnace. The current's still really low. Okay, but anyway, it's just a weird example. Okay, so now we're going to take that current back the way we always have been. This is delta. There's 0.8, so this is going to be more. So this is going to be 0.827 times root 3 times root 3, 1.433 amps. That'd be here, right? 1.433 amps. That is going to get split, so 1.433 divided by root 3. Looks like it's going to be 0.8727 again. Okay, and that would be right here, right? 0.827 amps. We're going to go across at a ratio 3. 0.827. I don't know what's going on with that. 0.827 amps. Okay. Divided by 3 because the ratio is 3. So 0.827 divided by 3. 0.276 amps. That would be here. 0.276. Okay. And that's also going to be 0.276, guys, right? Because it's Y. 0.276 amps. Okay. And now XC each. That's where this is going to come in handy. 73.78 ohms. All right, guys. Now, terrible. All right, guys. But that's how it's done. Okay, guys. So have a good one.